Hello, today we're going to talk just a little bit more specifically about the collision model. So let's review. There are three main components of collision theory. In order for things to react, they must, number one, they must collide. They must collide with enough energy, and they must collide in the correct orientation. So if we talk about this one first, just that they collide, there are a few things that affect how frequently they collide. And those things are concentration, temperature, and surface area. Now remember that increasing the concentration packs the molecules in more closely together, so they're more likely to collide and then will react faster. At higher temperatures, remember there's two parts there, so they're moving faster, so they're more likely to collide because of their increased kinetic energy. Also at higher temperatures, they're more likely to meet the minimum amount of energy, which we will talk about in just a few minutes. And then the third part with surface area, the greater the surface area, or the smaller the particles, the more space, just physically, there is for more collisions. So the reaction will go at a faster rate. So that second part of the collision theory, that particles must collide with enough energy. That minimum energy is called the activation energy. Now we're going to look at energy profiles a little bit more specifically later on, but if you were tracking the energy over the course of a reaction, so I'm going to say time here just to make things simpler, but you might not be measuring it in time. But if we're tracking the energy, you'll have the energy of the reactants and the energy of the products. Now the reaction might decrease in energy or increase in energy over time, but no matter what, it will require a minimum energy for the reaction to start. And that difference here, that's called the activation energy. Okay. So it's the difference between the reactants and what we call the transition states, or sometimes we'll call it an activated complex. That's the activation energy. Sometimes we call it the activation energy barrier. But it's like a hump that you have to get over in order for the reaction to go. And if you don't have enough energy, imagine it like a ball rolling up a hill. So if you kick the ball and it goes up, but you don't have enough energy, it's going to roll right back down. And the same kind of thing happens with molecules. If there's not enough energy, nothing happens. But those particles that do collide with enough energy will get over the hump and react. Now we can also look at activation energy on a Maxwell-Boltzmann distribution curve. Remember, the Maxwell-Boltzmann distribution curve shows the fraction of particles in a sample that are at any given energy. Okay. So if you look at this first diagram, this is a very typical Maxwell-Boltzmann distribution curve, but it also shows you where the activation energy is. Okay. So that's a barrier. Anything above that energy can react. So this shaded part here are all of the particles that can react because they have enough energy to cross that barrier. Everything down here in the lower range cannot react because it does not have enough energy. Now you can also affect the rate of the reaction by changing the temperature. So if you look at the bottom one here, it shows two Maxwell-Boltzmann distribution curves for different temperatures. The lower temperature, you can see the activation energy doesn't change at different temperatures. That energy stays the same for a particular reaction. But the area under the curve after that point, that all of those particles for the lower temperature, there's much more particles for the higher temperature. So at a higher temperature, more particles have enough energy to react. All right. Another thing that you should remember about changing the temperature for a reaction is that it's going to change the value of your rate constant K. So it changes your kinetic energy. It changes how many particles have enough energy to overcome the activation energy barrier. And it changes the value of your rate constant K. And then the third part of the collision theory is, of course, orientation. They must collide in the correct spot, basically. So these are just a couple of drawings to illustrate that. So let's say, for example, the hydrogen atom here has to collide with the bond in order for that bond to break and form a new bond with the hydrogen atom. So this is a successful collision because it's in the correct orientation. But if the oxygen end of this ion here bumps in instead, no reaction. Or I guess it could be chlorine, it doesn't really label. But whatever the atom is, if that bumps in instead of the hydrogen, then it won't react. Or if the atom bumps somewhere other than the bond, then it won't react. But it's very dependent on what molecules you have, what reaction's going on. So they're not going to ask you to like draw a successful orientation. It's just something, one of the factors that affect whether a reaction can occur. Okay, so it says, given the following reaction, which set of reaction conditions will result in the highest reaction rate, and explain in terms of collision theory. So it looks like, let's look at each one separately. So, well, actually, let's compare experiments 1 and 2. Experiments 1 and 2, it has greater moles, but it also has a greater volume. So the concentration isn't changing for either reactant because the moles are doubling and the volume's doubling. So the molarity, the moles per liter, stays the same. So you're not going to see any difference between 1 and 2, especially because it's at the same temperature. All right, but if we look at reaction 3, or experiment 3, the volume of the container has decreased. So because the volume is lower, the concentration will be higher because remember molarity is moles per liter. So if I increase the liters, I will decrease the molarity. And vice versa, if I decrease the liters, I will increase the molarity. So at a smaller volume there, you will have a greater molarity. So that means the higher concentration is going to have more collisions. And so experiment 3 will result in the highest reaction rate. If this is a free response question, please make sure that you're trying to frame your responses in CER, so claim, evidence, reasoning. Your claim would be that experiment 3 has the highest reaction rate. Your evidence, you could show the calculations for molarity if you want, or you could explain in words like, the moles per liter in experiment 3 is larger than the moles per liter in experiment 1 or experiment 2. And that's your evidence. And then your reasoning would be about the collision theory. The higher the concentration, the more likely the molecules will collide for a successful reaction, and therefore we'll have a faster rate.